Yes, okay, thank you very much for giving me this opportunity. This will be a relaxed lecture entirely on the Blackboard. Please ask questions at any moment. So I don't assume you've been following this story that much. So I'll try to be extremely uh, gentle. So yeah, let me discuss the title first. So we have two items here, massive high spins and Kerr black holes. So what do I mean by massive high spins? Well, those are particles. They point like with some mass and spin. And this spin is quantum. And well, to be safe, let's consider it to be larger than 0, and then it's higher. The word higher means larger than 0 for as far as this talk is concerned. So, sorry? Did I say, what did I say? Yeah. Oh, no, larger than 2. Yeah. Larger than 2. So it should be high. It should be, the spin should be higher than the graviton spin in the gravitational context. 2 is the border between high and low. So S is, of course, an integer. So we're talking about quantum spin in this context. And that means that, well, it's quantized in units of h bar, and h bar, you know, it's Planck's constant that goes to 0 in the heuristic classical limit. So on the other side, we have Kerr black holes. So those are normally extended objects. They also have mass, and they have a classical spin vector. So classical spin vector or pseudo vector. Let me call it A mu. So, or rather, S mu is the spin vector, but in the Kerr context, it's very nice usually to rescale it by a power of mass, and then it has the dimensionality of length, and then you can compare it with the Schwarzschild radius, and yeah, usually we have A smaller than GM for normal mass, for normal black holes, non-extremal. So yeah, and this is a classical spin. So of course, you know, here the expectation value of the spin operator for particles like this would be proportional to h bar s. And so if you want to make to go really from this to that, we need to take the classical limit where h bar goes to 0. So s has to go to infinity in order for this thing to be classically meaningful. So if you don't do that, if you don't take s to 0, then unless you do something else carefully, you will just get 0 spin, right? Classical spin will be 0. So this is so those are the two items in the title. So this limit, we started using it heuristically back in 2018 with Alfredo and Justin. More recently, with Rafael Aude, we wrote up how to formulate it less heuristically, more carefully in terms of coherent spin states. So then you're not taking the double limit, trying to leave this finite, but you cook up states to have a nice expectation value, and then you can phrase things in a very similar way. But in the end, you just basically get what we were doing back in 18 and 19. So yeah, so coherent spin states are. I'm using this word to juxtapose that to definite spin states, which we usually like in quantum theory. So okay, so this was just like a explanation of the title and of what I want to talk about. And so now let me talk about motivations to discuss all of that. So well, one of the things that like a major motivation in our community has been to use amplitudes for classical dynamics of well, rotating compact objects such as black holes. And well, that's why I'm sort of talking about black holes when I talk about massive high spins. So the identification is, of course, m small equals m large, and well, an expectation value of S as an operator equals a mu, where this is fully classical spin length. So this is motivation really relevant for gravitational physics. And the gravitational interaction is the interaction that is important in that context. So I would also argue that, well, there is also quantum physics reasons for considering massive high spin. So massive high spins, such particles, you might not have heard of them, but they really exist in nature. They are composite particles, and they don't even have to be unstable. So my favorite example is boron. It's so there's an isotope of boron that has a nucleus with spin 3. Okay, you can dig the ground, and the nuclei inside the atoms will be massive high spin particles. And they will somehow interact with the electrons in an effective way. So yeah, so you can in principle imagine an EFT for such particles. And I would argue that in this context, electromagnetic interaction is more interesting, whereas here, I guess, gravitational is more interesting. So of course, yeah, as I said, they are composite, so they are not elementary. So that means that we are using an EFT approach to describe some kind of physics at some particular scales. So you can imagine some scales that have to be much smaller than the mass of the particle. Otherwise, you're more likely to disintegrate the whole thing, and that's not great if you're trying to use a point-like approximation. So we can imagine having mass somewhere here, and then having a cutoff below the mass, and then this would be some UV cutoff. Or you can even conflate the UV cutoff with the mass, and just consider low energy interactions. So in this context, of course, if you understand that what you're dealing with in this context is an EFT, then you know that you should not expect a good massless limit. So it tends to be really, really bad. So and this is fine. This is not a problem because it's not elementary. And actually, in the electromagnetic context, S larger than 1 is already problematic. And S equals 1 is the usual, the well-known case of the spin 1 massive boson, right? The Proctor field, and we know that you can make it work. They even exist in the standard model as elementary particles, but they are phrased in terms of usually spontaneous symmetry breaking. So this is for motivations, as far as the motivations go. And let me now talk about amplitudes. So kind of this workshop is about mathematical structures in amplitudes. So let me show you some simplicity in the mathematical structure of some amplitudes. So the 3-point amplitudes for massive high spins, in principle, you can write many amplitudes, even at 3 points, for these objects. But let me call the nice ones HHH, because due to Arkani, Hamed, Huang, and another Huang from 17. So they wrote amplitudes, and I will not write the full expression. I just want to write the expression that, the part of the expression that I like. So imagine that you have a massive 3-point amplitude, right? Interacting with some, so imagine that it's a photon, for instance. Now, 0 here means just, it's a scalar amplitude. You can just compute it with a single Feynman rule. And they wrote amplitudes for spin S, for general spin, in the following way. So the full spin, massive spin degrees of freedom are encoded in a single, simple looking prefactor. Let me write the by parity. So by parity, the other helicity is written in terms of antichiral massive spinners. These amplitudes were written and called minimal coupling in that paper. Since then, we learned that this idea clashes with what other people tend to call minimal coupling. So maybe so that's why I actually like to write HHH instead of using minimal coupling. Right, exactly. So this paper, one of the points of this paper was to introduce the massive spin helicity formalism, and along the way they introduced these and more amplitudes in that formalism. So let me talk about this formalism a little bit. So these are massive massive spinners. So one here is corresponds to momentum P1 that has a mass. And so, of course, I've hidden structure. So as a spinor bracket, it's a SL2C contraction of the usual Weil indices. So let me write it upstairs here. But also, I made implicit an index. Let me call it small a. That is an SU2 index. So this is SU2, and this is SL2C. SL2C is the same index as we have in massive spinor helicity. And so you could, in another notation that makes indices explicit, you could write this object like that. So it's a 2x2 complex matrix. And the bispinor corresponding to the momentum can be expanded in such. Well, let me write it in this way. Can be expanded, and by convention, I put the little group index inside the bracket, and the SL2C index outside the bracket. Right? The bracket still tracks the SL2C representation. But on top of the, but instead of having helicity, the little group being just phase transformations, now it's a full SU2. So by that I mean that this amplitude is actually, it depends on 2s of the 2s indices corresponding to the Lillo group of particle 1, and 2s more indices corresponding to the little group of 2. Let me put it downstairs, right? And then I can open this up. So now I'm opening up this notation, but you know, the object is still arguably the simplest object you can write. The only question is, of course, we could have written this for plus helicity and this for minus helicity. That's not necessarily obvious. So when I write this, I actually mean, well, sometimes I even put a symmetrized tensor product symbol here. So what I mean is that I take a spinor product. It has 2 indices, little group index for 1, a little group index for 2. Well, there needs to be 2s of them. Well, let me write 1, 1, 2s, 2s, right? And they all symmetrized. They symmetrized with each other, of course. All the a's are symmetrized among themselves. All the b's are symmetrized among themselves. So that's the definition of this bracket. Now you see that it's not an entirely trivial spinor product, right? It contains a lot of information about the spin degrees of freedom. This representation, so it's a 2s symmetric representation. It's a irreducible representation of SU2. And the easiest way to see it is just to imagine that, okay, every A can take values 1 and 2. Well, they can all be 1s. They can all be 1s but 1. And it doesn't matter where you put this 2, because it's all symmetrized. It can all be 1s but 2 2s. And again, I can just put them at the end because it's all symmetry. And so on, up until all of the 2s, all of the indices are 2s. Right? And in this way, you just fill in all the 2s plus 1 degrees of freedom. So that's the essence of massive spinor helicity formalism in a nutshell. Do you have, yeah, please interrupt me at any point if I'm going too fast. Or maybe I'm going too slow, and then maybe you can nudge me in the direction of going too fast instead. So very good. So these amplitudes, they were written in this paper as just the nicest possible amplitudes by some massless high energy limit or massless limit considerations for a quantum spin-s particle. And then later in the paper with Alfredo and Justin, we realized, well, there was already some hints for these amplitudes also somehow being related to Kerr black hole. And in the papers with Justin and Alfredo, we also realized that when you take the classical limit, you can rewrite these 2 amplitudes as exponentials. So they depend on the helicity. The sign here sort of depends on the helicity. But in the classical limit, you know, A is now a classical spin length of the object that you are scattering. You can phrase it in such a way, so classical limit, that it becomes this structure at this level, it looks like a binomial structure. Right? It looks like a power of something. But if you phrase depending on how you phrase it, actually it doesn't matter how you phrase it. You can phrase it in terms of s to infinity, or you phrase it in terms of coherent spin states. You end up with an exponential structure. So the dependence on spin here, right? You usually have amplitudes looking like a scalar particle, and then there's some expansion in the spin variable, and the spin variable, now classical, corresponds to spin multiple expansion of your object. And Kerr black holes have a very striking spin multiple expansion. It's not random coefficients. All the coefficients are basically 1 over factorial of something, right? And then they all resum into a nice exponential. So we realized that, and that's the main reason why there is a 2, in the title. At 3 points, we know what the amplitudes are at the quantum level and at the classical level. And at the classical level, so this exponential connects very nicely to the Newman-Janus shift, which is discussed in the paper Arkani Hamed, O'Connell, and Huang, 19. So, but in principle, that shift is the way the Kerr solution was written in the first place. People were struggling to write the spinning black hole solution for decades, and then there was some, Lionel can correct me if I'm wrong on this classical story, but I guess the story is that people came up with a way to construct solutions to the vacuum Einstein's equations by constructing complex, by shifting in the complex, and then still reading off totally nice and real solutions to those equations. And one of those was Kerr. And so just in the way the Kerr solution was written in the first place, the dependence on the spin variable was encoded in the shift of, let me write it like z going to z plus minus ia. So now this is the coordinate, and then it goes to some kind of complex coordinate. And a is the length, is dimension of length, so it just adds up very nicely. So yeah, so that is just to say that this exponential structure of of Kerr multiple of the Kerr spin multiple expansion can be just thought of as the consequence of the original way of writing the Kerr solution. So very good. So now I want to go further. So this was an older story from 3 points. Let me put it upstairs maybe. But then some people, including me, realized that there are some nice amplitudes at endpoints. I'll use a very similar notation. Oh, and by the way, yeah, here I was talking about photon for some reason, but then the same structure can be used for graviton, right? So actually, I didn't write the spin zero part here explicitly because that's different depending on which interaction you're considering, right? If you're considering gluons, then you would even have a gauge theory structure. But I'm talking here about the massive spin structure, right? And this is, the spin structure in those amplitudes is the same. And now I'm also talking about similarly different theories of interacting massive high spins. And for spin zero, there is an amplitude at endpoints, first derived by Forty and Sauer, right, in 05, and Ferrario, Rodrigo, Talavera, I think also 06. So these amplitudes at zero spin for identical helicity, say gluons, were derived quite a while ago. But it turns out that there's a nice family of general spin amplitudes, also identical spin, identical helicity for the massless guys, So now we're talking about an amplitude of this kind that have just the same structure, right? So this wasn't obvious at first, but for zero spin, these amplitudes were derived a while ago. Then for spin half in QCD, they were also derived. I derived them in 2018 using this formalism in exactly this form. But even back then, it wasn't obvious it would generalize so easily. But yeah, it's an EFT. So as soon as you're in the high spin realm, you are allowed to add contact terms. The non-trivial thing here is that you are allowed not to. And by this, I mean that what you need to derive these amplitudes for general spin is a BCFW recursion. And when you use it, you assume some boundary behavior. So when you do the BCFW shift at infinity, you assume some nice behavior. And sometimes you cannot get away with assuming that at all, right? Sometimes you assume it, and then you get nonsense that does not even obey your assumption. So here you can assume it and get this answer. So the derivation goes through just in the same way as in QCD. It's embarrassingly simple. At endpoints, you can just derive these amplitudes in the same way as you can do in QCD, or I think maybe even you did it using also BCFW recursion in the spin 1, in spin 0 case. Another reason why I took those amplitudes seriously was that usually you choose a shift, and then you can choose another shift. And here, these amplitudes are stable because you can derive them using a massless shift. Massless. So this is when you shift to gluons, say, or gravitons, or you can use a massive massless shift. So I really took these amplitudes seriously when I realized in this paper where we were using the massive massless shift that I still get the same answer. So for some reason, it started to look like the identical helicity sector was favoring a very nice spin structure for massive high spins. A0 depends on the theory, and it's not too complicated. Yeah, I mean, I could have written it, but I think the easiest way to write A0 in gravity, for instance, is to use the KLT double copy from gauge theory. So this is a surprising simplicity where the spin structure just factorizes onto this nice 3-point-like exponential-looking structure. Also, in the classical limit, you can write this as a similar exponential, there. So the left-hand side of my talk is massive high spins, which is EFT. So it's an infinite kind of space of effective field theories where you don't necessarily expect any simplicity. But here, these amplitudes hint at some very simple massive high spin EFTs. So they seem to exist in the huge space of general massive high spin EFT. So now I would like to go back to field theory. Yeah. So yeah, David. Well, the scalar amplitude is not even an EFT. It's a well-defined theory, right? With a good UV limit. It's just a massive scalar. Yes. Sorry. So when I said depending, so yeah, this does not depend on the theory. It only depends on interaction. So by depending on the theory, I mean, are those particles photons, gluons, or gravitons? Those are the three cases that I tend to be interested in, right? So depending on if those are gluons, then A contains some color ordering. If they are photons, then A has the sum of all color orders so that you project from the non-abelian to abelian. If those are gravitons, then A also contains the double copy structure from gauge theory. That's the simplest way to write it. Or you can use another method. Oh no, the zero spin amplitudes are not in not EFT amplitudes. They are usual minimal coupled. Yeah. But I'm talking about in this realm. You, in principle, live here. But some amplitudes are so simple that their amplitudes just factorize onto those. Let me call this stuff like elementary, right? This is elementary because all you did was give mass to a scalar. So they factor this stuff that doesn't have to be any simple. It's just EFT of something very complicated. But some of them turn out to factorize very nicely onto like elementary looking amplitudes. And all of their nastiness sits here, right? The massless limit still looks bad, but it's the worst kind of bad. It's the best kind of bad. Yeah. No. Yeah, maybe, yeah, if we're talking about other helicities, so a lot of work has been done recently, including by me, on the minus plus helicity. So this otherwise called Compton amplitude. So this Compton amplitude is kind of funny because it starts being interesting in the two-body problem at one loop, right? So at one loop, you start being interested in triangular coefficients where you need the input at tree level from the Compton amplitude. And this minus plus, unfortunately, if you use BCFW recursion, you get onto the answer that contains let me write it like this. It contains a spinor product, just a massless spinor product, to the power of, in gravity, it would be 4 minus 2s. So it's fine until s is smaller than 2, but as soon as you go to high spins, then you get a pole. This becomes a pole, and it's a pole in the complex plane that has no physical meaning. So BCFW applied to minus plus helicity shows you that you're not doing all the work that's needed to get to something sensible. And I'm going to get to that later. So let me now do a crash course on high spin field theory, right? So now we have a motivation from amplitudes to look into, this body of work that's been lying around. That's massive high spin field theory. So let me start with the old method. Let me call the old method what people have been using since Fierz and Pauli in 39. So and then I guess the seminal papers by Singh Hagen in the 70s, yeah, 74. So in this method, let me also consider the integer spins for simplicity. So you consider a field now. We're not doing on-shell stuff anymore. with S vector indices, and they all symmetrized. Well, in order to be irreducible, it has to be traceless, and you know, high spin people even just write it as phi to the power of S, just indicating that there's hidden indices every time you write a phi, such as this. So, so what were the problems already pointed out by Fears and Powell in '39? So the main complication is obvious. If you count the number of degrees of freedom, you just have too many. So you want 2s plus 1, but you get, actually I don't remember how many exactly you get, but you get way above 2s plus 1. And even for s equals 1, you know that there's a problem, right? You get 4 degrees of freedom because nothing to symmetrize, it's just a Proctor field. And you know that it should be 3 degrees of freedom for the spin. Let me call it V mu. Right? Already in the Proctor case, it starts building up this problem. And so you know, and the solution is to impose transversality. Transversality. So you impose something like this. And then it's good. Then you've killed the unphysical degrees of freedom. And you know that it works for Proctor. But the difference between Proctor and high spins is that for Proctor, you can get equations of motion such that transversality comes out of them naturally. You don't have to input it in some ugly way. But for high spins, there's no nice way. And what people have been doing, what they're introducing auxiliary fields, let me call them phi. Now, let me use R, because it's not spin, it's actually just the rank of auxiliary field, it's not physical spin. And they, back in the day, they were introducing a tower of, from 0 to s minus 2, a tower of spins, a tower of rank R auxiliary fields. And all of this was just needed to, in the end, impose transversality on the equations of motion. And now I'm still talking about free field theory, right? So, so the interactions may, in this approach, may still source the unphysical degrees of freedom. So, and this unphysical degrees of freedom is the main, has been the main problem in this field for decades. For spin 1, you get the Proctor Lagrangian. You don't even have to introduce any auxiliary fields. You may, but you don't have to. And there's a field strength equation like this, right? And then just multiplying it by a gradient, you get 0 here, and then you get transversality on the right-hand side. So something like Maxwell's equations in the massive case just imply transversality magically. That's one of the reasons why spin 1 is still not massive, is not higher spin. Very good. So let me start erasing stuff. So this is the main problem on physical degrees of freedom. And all literature on this subject hits various complications very soon. There are classical papers talking about superluminality. Let me. 1, 2. Okay. Huh? I mean it. All right. Okay. Yeah. I only have 4 boards here, so I have to erase at this point. So okay. So there were, of course. Yeah. So there were more papers even looking at seeing superluminality in high spin amplitudes, and high spin at that level was 3/2 coupled to electrodynamics. And that's very bad, of course. So, but then Zinoviev came up. He was doing a lot of massless high spin theory on ADS, but then what was born was a new method, and apart from the physical field containing physical degrees of freedom, he introduced a new set of auxiliary fields. So now it might look even more horrible. So now he has, the tower goes not to S minus 2, but S2 minus 1. So moreover, these fields are now double traceless, which is a less stringent constraint, because the trace does not have to vanish, only double trace has to vanish. So he put even more auxiliary degrees of freedom into the problem in his method. But his method was informed by massless high spins, and what he gained was gauge symmetry. So gauge invariance a la Stuckelberg. So that, and now when you have a gauge invariance principle, you can ensure, so it ensures that there's only 2s plus 1 physical degree of freedom in the problem. So let me write what it looks like. I'll use this high spin notation where I don't write all the indices. So imagine that you shift it by something. So you have a gauge parameter that has rank r minus 1, and it gets shifted by a derivative that's symmetrized. So this is very similar to the massless gauge symmetry. In massless free theory, you have this. But we are having a non-zero mass, so he introduced additional shifts. So this is just a shift by a rank, where a field, rank R field is shifted by a rank R gauge parameter. And then there's even a trace term. So eta is the metric with 2 indices, and they are symmetrized with R minus 2 indices of another gauge parameter. So, okay. And these are just coefficients. He worked them out, they're combinatorial. So an important thing here is that for the physical field at rank S, there's no shift. Otherwise, you would be able to shift the physical field to 0. So that's the method he came up with in 01, basically. And the beauty of this method is that not only you can formulate now the free field theory in this way, but you can start introducing interactions. So interactions, you can just start introducing some interactions in a way that must respect this. But you are even free to adjust this together with the interactions. So as long as at each order you have a consistent gauge symmetry, you still guaranteed 2s plus 1 degrees of freedom. And yeah, you can do it consistently. Now you have, this is a method that you can use. And we did. So in this method, so there's still a problem, of course, that this is very non-trivial. Non-trivial refinement of action and d phi. So in this sense, it's sort of good progress, but the problem, I think the problem of this method can still be demonstrated by the fact that there were many 3-point results in the literature, just a multitude of papers using this for 3-point interactions, but no 4-point. 4-point. So new 4-point results we managed to obtain with Lucille, Marco, Henrik, of course, and Paolo, and Zhenya. So we learned about this method from Zhenya, Skvortsov, and we started using it. And we are amplitudes people after all, so we got to 4-point results in this method by not doing the full version of it, because we were doing like currents. So the off-shell part we only left on one leg, and that allowed us to go through farther than usual field theory people did at the time. So and it's pretty hard. So the main complication that we didn't like about this method, and well, it's nice because it works. But the hard part is that it's hard to be generic in spin. Say it again?
What were you doing there? EM or Kerr?
Both, actually. Yeah. So, okay. Okay. And now we did spin 3 as well. Yeah, we did a bunch of stuff. I don't. In the end, we produced an amplitudes with that. I'm going to. So in the the paper, the long paper on this that we have in November last year does just gauge theory, but we also did gravity, but we didn't explain it very, very carefully because the long paper only deals with gauge theory. So anyway, now let me talk about the new approach. So all of this discussion was needed for me to tell you, for you to understand that this problem of unphysical degree of freedom has been for decades. But when we were working with Zhenya, and I showed him those endpoint amplitudes, we realized that there's a better way. So in 4D, so this is only, it's chiral, so it works in 4D. Everything else before, like this stuff, works in D dimensions, so that's nice. But after all, we're interested in 4D. And in 4D, you can have something that's called nowadays the chiral field method. So our approach is very simple. So take a field, not to be in this tensorial representation, but let it be in the chiral spinor representation. Now you have 2s indices instead of s of them. And then you symmetrize the spinorial indices. But the beauty of it is that such a field, if you imagine that it's a real field, it has the same counting. It has the 2s degrees of freedom by the same counting, right? Because the SL2C index also has two components. So there's no unphysical degree of freedom here unless you introduce them by doing complex conjugation, right? So if you complex conjugate this, you will get the antichiral field, and the number of degrees of freedom will double. But we say don't ever do that. Treat this as real. Treat as real. It's just a mantra, but in actual calculations, when you write the Lagrangian, just never write this. And that turned out to be a way to not ever worry about unphysical degrees of freedom. So here it's easy to write consistent general spin EFTs.
So did you want 2s plus 1 complex or 2s plus 1 real?
I wanted 2s plus 1 real. Yeah. Yeah.
So here complexification.
Yeah. Well, the complexification is because we are using the spinor representation of the Lorentz group. The Lorentz group itself is real, but the spinor representation is complex. So
But there's a kind of implicit. So the point is that phi tilde is determined by phi. It should also be the complex consciousness of phi.
yes.
So there's an implicit reality condition that might.
I think the reality condition can be thought of as a reality condition maybe in 2-2 signature, but in Minkowski space it translates to just don't write antichiral. Yeah.
I can see that
I think so. Yeah, we can discuss how far it can go. But the point here is, yeah, now it's sort of trivial. You can just write whatever you want, and you will not have the problem that people were struggling with for decades. But you will get a chiral theory. So the theory that you write with chiral fields is chiral unless you do work. So everything is chiral by default, right? You wrote things in a chiral way. The interactions can still be non-chiral, right? You can imagine a non-chiral theory where you did a chiral field redefinition. Your theory will start looking chiral, but in fact, it's still the same theory. So it doesn't mean that we cannot write non-chiral theories, but the chirality now, well, say parity now is non-obvious. That's the main caveat for this method, and well, it's right in the name, right? You're using chiral fields, so the work now is imposing parity. And sometimes you might not even want to have parity. In the context that I'm talking about here, Kerr black holes, well, you want parity. So we've been dealing with that. Right, so I think the best way to talk about this method in more detail is to write some actions now. So I'll write some actions. And by the way, I'm not sure about the time limit, but the point is that I can, right? I can stop at any time, right? I've already said the main the main thing. We have a chiral field method. Everything else is applications, more or less interesting depending on your. Yeah. So yeah, let me talk about explicit actions now. So I want to write an explicit action that depends on this field that is now a chiral field. Well, I'll write. Well, as far I guess let me just do gravity. So yeah, so let me write first a free field theory. With explicit indices so far. I'm not sure I need really to look. Right? So, okay, this is already some Lagrangian. You might think it's a scalar Lagrangian, but it looks indeed, it indeed looks like a scalar Lagrangian. But this is the correct Lagrangian for the free field theory. What else can I say here? The main information about this being higher spin is in the fact that these indices are not some internal indices. They are space-time indices. So as soon as I turn on gravity, and I can turn on gravity to start with in the most naive way, just by making these derivatives covariant, they will talk to this derivative. So when I write this, I mean that when I take this derivative, I actually, well, take the usual derivative, but then I add a spin connection contracted, and it actually does not matter where I contract it. Something like that, right? So that's the most naive way to turn on gravity, the gravitational interaction for these fields. Omega, yes, yeah. Oh, 2s, well, it's just, yeah, it has to act on each index, right? So indeed, for spin half, the normalization is that it's 1. So it's a spin connection. Maybe it's a factor of 2 corresponding with respect to some other normalization. Let me write it. Yeah, actually, I have a. Yeah, exactly. Because they're all symmetric. It doesn't matter with which I contract. Yeah, that's right. So yeah, and the spin connection written in tetrad indices would be related to this spinorial spin connection by the usual sigma matrices contracted in the following way. Yeah, that's the explicit normalization. Well, sorry, yeah. Here I'm using A, B now for tetrad indices. Maybe I put a hat on them. Those are not little group indices anymore. Well, actually, I think it might be even nicer to discuss for a moment the case where the gauge theory case, because then I can go back to the amplitudes that I erased, unfortunately, but still. So in the case where we're doing this, and actually let me now do this and use spin helicity notation for fields now, because it's too many indices to write them. Why not write stuff like this, right? So imagine this action as a complete action, right? Here I was not writing everything yet, but imagine that this is the complete action in gauge theory, in non-abelian gauge theory. You have color ordering, everything. But now this covariant derivative has nothing to do with the space-time, right? It is just in the internal internal space. So in fact, it's trivial to write all of the tree-level amplitudes for this theory. So all of the tree-level, so for this theory, all of the tree-level amplitudes, let me 2s, 3n, for any helicities, because helicities now don't matter much in this, they will all be this. Because, you know, as far as gauge theory is concerned, this is just an additional flavor index. So the amplitudes that I showed before for identical helicities, sorry. Yeah, so they, the ones I showed had this for plus helicities and that, that for minuses, right? But now I have this for all helicities. So it's a very chiral theory. But it's a theory that is trivially related to this massive scalar, massive gauge scalar. So I've managed to write a Lagrangian for a massive higher spin theory to all orders in the points, right? It used to be 3 points. We got 4 points, but actually this is n points. I know it's just so simple that it's embarrassing, but it's an n point, and it's consistent in the sense that there's no unphysical degree of freedom generated, and all of the degrees of freedom that are related to spin are just in this chiral factor. So I think it's just a very nice way to show that you can use this method to get some amplitudes very directly. Yeah, maybe I didn't explain exactly how you get this factor. Yes, David? Say it again? Yeah, well, I treated them as real because this is a chiral spinor product, right? So I never introduced the... Um, sorry. Well, for spin 0, it's phi squared, right? It's just, it's literally the... mod phi squared. Oh, okay. Yeah, this is, yeah, that's a nice thing that is somehow confusing, was confusing. So this, when I consider gauge theory, I still consider phi's to be real, but I imagine a real gauge group. You can consider SU2 to be embedded in some real. Another way to think of this is, well, you can just consider SON instead of SUN, or you can think of introducing two imaginary units. So one imaginary unit is something that we tend to use, so that there's a complex related to SL2C, right, to the representation of the space-time group. But there's another complex that doesn't have to be the same complex structure that's related to the gauge symmetry, right, gauge group G. So the representations of the gauge group don't necessarily have to obey the same complex structure as this. So you can imagine decoupling those. That's another like more abstract way to think about those things, I think. So in that's the sense in which I don't complex conjugate phi in this sense, but maybe you can complex conjugate phi in this sense. So in particular, you can imagine writing SO2, right? SO2 is U1. This is the electromagnetism, but nothing prevents you from writing all electromagnetism as in terms of SO2 gauge group with real generators. So yeah, that's like that's a nice question. There's another nice feature here is that, you know, this phi times phi, it's for spin half or any non-integer, any half-integer spin. This is a spinor product that's antisymmetric. So if phi is a field that is bosonic, then it vanishes. So this is 0 for bosonic field for half-integer spins. So this field approach tells you exactly that if you want something non-trivial, well, you'd better have fermionic statistics for half-integer spins and bosonic for integer spins. So it's built in directly just from the spinor product antisymmetry. And for spin half, by the way, this goes back to Chalmers and Siegel. Chalmers and Siegel in 01 at least, they have a series of papers where they do chiral, they use chiral fields for the standard model, in particular for QCD. For lower spins, so we found that it has already been known, it just not many people were using that approach. So it's a field redefinition corresponding to the usual standard model fields. It relies on you know, normally you would you imagine a Dirac fermion. It has the chiral and antichiral spinor, but then basically this phi of mine, I think it's 1 over square root of m chi, and eta tilde, so the antichiral part of the Dirac can be integrated out. It's sort of one step exercise. So, right. Any more questions? Exactly, yeah. It doesn't. No, I wrote a theory. It doesn't have to be the theory that I was interested in the first place, right? My motivation came from Kerr black holes, and we know that, first of all, Kerr black holes, an effective theory of Kerr black holes has to be parity invariant. What do you mean? I mean, sorry, no. I'm saying that these amplitudes are generated by this action. Yeah, that's all I'm saying. So that's, yeah, this is, I just presented you a way, a simple example where this chiral field approach is used to formulate a theory at endpoints, at arbitrary multiplicity. To my title, yeah. Yeah, I can, yeah. I just wanted to show you an example where you can really understand how this method works. And so to the extent that you can even write all the amplitudes. It's not supposed to be true. It's only, yeah, so I only got the nice amplitudes that I wanted for the all plus helicities. Yeah, for the everything else is just completely screwed up. But at least, as far as the massive high spin literature goes, this is the first endpoint result. Yeah. Exactly, yeah. And now you can say, oh, I'm actually, how did I turn on interaction? I turned them on by covariantizing derivatives. I can also just introduce more stuff. For instance, I can write f phi f, where f is the self-dual spinor contraction. So you can just put it as an additional interaction. And in fact, for spin half, this will be QCD. It was, you can go back to Schelling and Siegel and see that what they wrote was this plus this plus this. And that was QCD. You get even QCD. So QCD is a non-chiral theory. And it has an additional interaction with respect to this. And indeed, it fixes things. But then beyond lower spins, you have to introduce a tower of stuff, right? And then with one F or more field strengths and so on, you are allowed, in an EFT approach, you are allowed to just start adding anything you want. The advantage, still, the development is that now you don't have to worry about physical degree of freedom. And now, yeah, let me get to, yeah. Which one? The kinetic term, yes. Mm-hmm. Dotted indices, yes. No, yeah. Dotted indices are always contracted, yes. Yeah. Yeah. You can sort of trade things slightly. Pardon me? Well, what I'm adding here is this single term. Well, for spin half, it's the only term that's needed to fix parity, turns out, if you just compare with Chalmers and Siegel. But yeah, it's just something that you are allowed to add. In general, the coefficients here will be free because it's an EFT. You can try to match them to some multiple expansion, and then they will become not free. They will become some numbers over masses because you will have higher and higher dimension operators. Yeah, it's sort of the, there's already a term like this. If you rewrite this as d squared plus m squared, right? I could have written it in this way. right? And then there would be indeed a term of this kind. You're completely right. Yeah, and the free equation of motions are, of course, just Klein for Gordon. So there's nothing to really do, right? The Dirac equation for spin half, for instance, is needed to project out the two unphysical degrees of freedom that you introduced by using the Dirac field. Once you integrate it out, the antichiral part of the Dirac, you don't need the Dirac equation anymore. You only need the Klein for Gordon. So phi q, yeah. In the context that we're interested in, where these are heavy composite particles, I'm most interested in the interactions with some field, massless field, such electromagnetic. No, I don't want to. Exactly, yeah. It doesn't mean that I cannot introduce that. Of course, I could, but in the context so far, we have not been doing that. Yeah. So now let me be quick about the applications to black holes. So I'll write another action. Maybe I'll just erase stuff from here. So I've already actually screwed up my formula. So now in gravity, now that we know more or less how this method works, in gravity, so I have this, I switched on in a chiral way, I switched on the gradatial interaction in a very chiral way, but then I have to account for the chirality. So what I did, what I'm going to do here is just write 3-point action. So that you see what kind of stuff I can add. So I don't want to change plus helicities. We've already discussed that, right? The plus helicity structure is already of this kind. Even for gravity, it also works similarly. It's just harder to see because there's some non-trivial interplay between derivatives and indices. But the new interactions, I'm allowed to introduce derivatives, of course. But the derivatives, as I said, well, once you introduce the derivative, you get an antichiral index. So once this antichiral index is introduced, you have to contract it with another antichiral index, and this index will come from another derivative. K beta k. So there's no problem in writing that. But on top of that, well, there's some interactions. I want to introduce this as an interaction. So I want to, I'll introduce a spinner here. It has 4 indices that are all actually symmetric, but I'll write them, some of them up, some of them down. And so I've done contractions. Some of the stuff is already contracted. K indices are already contracted. The K, 2 more indices, K1 plus K2 are also contracted. And then everything else is contracted with Kronecker deltas that I can, write K plus 3, alpha K plus 3, beta 2s, alpha 2s. And in principle, you are allowed to add R squared terms. So this, but what I've written is a 3-point action that, from which you can now derive in a totally field theoretic way using Feynman diagrams these 2 3-point amplitudes. So this is like the HHH action in the chiral field approach. 4 spinning indices. Yeah, this is like the, sorry? Yeah, the wild spinner, yeah. Well, I use R just because, I could, is it C? Yeah, it's usually C. Um, exactly, yeah. Exactly, yeah. So I will, I wrote something very simple, but then I have to account for my chiral approach by introducing more interactions that fix order by order parity. Oh, it doesn't turn k. I said plus order r squared. You know. Oh yeah, yeah, you could. You could. So what I wrote here is specifically the action that matches the HHH amplitudes, which are nice. That have they actually have the lowest number of derivatives that you can add by preserving parity in this context. It's still quite a lot of derivatives, but yeah. So this is so far I've been talking about 3 points, right? It's still hopefully you've been convinced that even 3 points at in the highest spin context is non-trivial. Yeah, let me not write the explicit 4-point amplitudes because let me just say it. I've already pointed out that when you consider a two-body problem, there will be triangle topologies that will be sensitive not only to 3 points, but also to the 4 points. Well, yes. So Andres and friends have not been doing proper quantum high-spin theory. I think everybody agrees on that. So what they've been doing were exactly. So they've been only worrying about the classical limit, whereas this is actually a quantum field theory with the degrees of freedom that don't go haywire. Yeah. Then another thing, yeah, another thing maybe. So Zhenya, with a student, has written a paper where, for lowest spins up to spin 2, he has produced explicit. I think it's still in free field theory, but still explicit field redefinitions that go from some more conventional free field theory non-chiral, right, in terms of either, well, I've already pointed out for Dirac, then you can do the same for the Proca. For the Proca, it's even not that hard to guess that for a Proca, this phi alpha beta is basically the field strength, the self-dual field strength of the massive Proca boson. And so he produced also for the what is it, spin 3/2 for the spin 3/2 field and for spin 2 massive field. He also produced the chain of field redefinitions that you can do to obtain this kind of actions. But then interactions are more complicated, and of course interactions are very complicated to add in other approaches. But here it's much easier to add interactions. So to conclude, let me just say that in this collaboration last December, we put out a paper, a PRL, that deals with the 4-point gravity amplitude, and we've produced a quantum amplitude and its classical limit. The amplitude was motivated by this construction, by massive high spins. So, and this action led us to consider some particular functions with nice classical limits. They turn out to be what's called in the mathematical literature complete homogeneous symmetric polynomials, and we use them to construct the ansatz for the stuff that is not necessarily captured by this approach, because the approach is still, it's agnostic about what you're trying to describe. You still have to input what you're trying to describe, and some of the stuff was already known, like at 3 points, we know what the poles should be, so we know the starting point, but this stuff is still subject to some constraints. You have to introduce some constraints. And we introduced a bunch of constraints, some of them heuristic, some of them were motivated by the partial data from the Tucholsky equation solution obtained by Bautista, Guevara, Kavanaugh, and Vines. And in the end, we got an 4-point amplitude, so both quantum and classical, that capture to all spin orders some piece of their solution. So it's conjectural if it's to all spin orders, of course, because they haven't produced an all spin order result. But we've we start seeing that our ansatz, motivated by this approach, seems to only need like a little bit information, and then the other stuff that they gave us was lining up nicely. Only a part of it, though, because they have the solution that they produce has tags on some pieces that come from some polygamma functions, and those are weird. We cannot get them so easily.
That's the other paper, right?
Sorry?
That's the other paper.
Yeah. In the
For your eta equals.
yeah. So they have they produce in 22. They have a paper. They produce an amplitude to lowest orders in spin, to some orders in spin, 6th order in spin, and they have tags alpha and eta. Eta tags the terms that are sensitive to the boundary conditions at the horizon of the Kerr black hole when you solve the Tucholsky equation, and alpha tags some contributions that come from some polygamma functions that they have to analytically continue in a non-trivial way. So they were not sure they were doing something correctly, so they tag them, take the terms that came from that source by an alpha, which should be 1 if they were doing everything correctly, but just in case, they tag them. And so we get the result very nicely for alpha equals 0, eta equals 0.
So the new paper by Fabian, he says that
Yeah.
it has to be 1, right?
Yeah, now he says alpha should be 1. Yeah, and now the alpha equals 1, we don't get to all orders. We can, of course, since it's an EFT approach, we can, of course, reproduce everything that other people give us. Here we were sort of trying to not just, take input and get stuff fixed, but also try to guess if somehow the field theory knows more about those amplitudes than we necessarily has to.
So how much can you predict from your theory?
How much? Well, as I say, the Compton amplitude for alpha equals 0, eta equals 0, we think we have to all orders in spin. Does it? The question is it a physical thing from their point of view? Well, some of the authors of that paper in 22. So it's the paper that I'm talking about is Bautista, Kavanaugh, Guevara, Vines. Some of them now think that alpha equals 0 is not a physical limit, right? I think some others might not even be on the same page on this. You are talking about a different paper that's later, and that only has Bautista.
Alpha equals 1, right?
Fabian says alpha equals 1 now. So there's still a controversy basically about this 4-point, but at least we have a this 4-point controversy about the Compton in the classical limit made us actually dig into the quantum higher spin theory and find a new approach that solves a long-standing problem of unphysical degrees of freedom. And we also use it for the original motivation and get some results. Controversy continues at a higher level. Yeah, thanks a lot. I used up all my time.
So where is the Kerr?
Where is what?
How close are you getting to Kerr? I mean, I didn't see much beyond the 3 points.
Yeah, well, formulas get longer and the time gets. I can write an amplitude that we consider to be this alpha equals 0, eta equals 0, and it's a 4-point amplitude, right? It's.
I see.
Yeah.
And does that have a Lagrangian avatar?
Yes, yes, it has. Well, actually, I think we didn't put the Lagrangian avatar in the paper because we wanted it to be short. But yeah, of course, once you this approach actually makes things quite straightforward. So any amplitude that you can write a Lagrangian for it. It's just a question of basically solving Feynman diagrams for the stuff that you know, and then fixing the coming up with a contact term that matches the on-shell contact term. And this approach is very close to the on-shell notation. So yeah, it's basically, at this point, it becomes a reverse engineering. And what I wrote is also reverse engineering, right? The amplitude was written in 2017. This action is just an off-shell action that reproduces the 3-point amplitudes. It's reverse engineered.
And then the 4-point amplitude, you've got opposite helicities on the two.
Yeah. I'm talking about opposite helicities. The identical helicity still has either this or this. Yes. Yeah. So we know. Them we know. I think everybody agrees that those are the correct Kerr 4-point amplitudes. Unfortunately, in the two-body problem, they vanish in the classical limit. So the nice amplitudes with this structure, they've been such a nice inspiration to look into this. But beyond 3 points, they don't matter in the two-body problem. Okay, thank you.